We start this afternoon with the third session of the course on Post Lie algebra by Professor Dekimpe.
Okay, thank you very much. So maybe before I really start, let me answer now for sure the question that was asked yesterday. So it was asked whether or not simply transitive action is the same as a sharply transitive action. And yes, indeed, so this is correct. So what I expected is true. So I announced that from now onwards, I will more or less try to fill up this scheme, saying that when can we expect, when or when not, can we expect a Post Lie algebra structure given the algebraic structure of G and of N. So the idea is to start filling up this scheme. And so we will consider several algebraic properties of both G and N. And so the first thing that I will do is consider the case where N is abelian. So I already translated this. So first of all, the case when the Lie algebra N is abelian. And so once again, this means that if you have a pair Gn where n is the trivial Lie algebra, all brackets are 0, this admits a Post Lie algebra structure. This was the case if and only if the Lie algebra G with square brackets admits a left-symmetric structure. And let me recall once more the two conditions for this. So this means, first of all, that the bracket of x and y can be written as x times y minus y times x. So we have such a product. And if we look at what's happening when we multiply a bracket with z, well, this should be xyz minus yxz, or you replace this by the left symmetric property that the associator of xyz has to be the same as the associator of yxz. So these are two possibilities to write this down. So this is the situation that we have. And I will not explain too much about this situation. Left symmetric structures have been studied for a long time, and one of the main results dates already back to the 70s. So this is the result by Jack Helmstetter, and this was published in 1979, so already a long time ago, and it says the following: if G is a semi-simple Lie algebra, then G does not admit any left symmetric structure. Yeah, and the proof of this result is rather long and technical. So Helmstetter induces a kind of radical, and then he shows that if you have a left symmetric algebra, this radical is somehow non-trivial, and that allows us to show then that G cannot be semi-simple, and semi-simple in this theorem also includes simple. So this is really saying the results that like we are looking for. We have an algebraic property, G being semi-simple or simple, and then we can conclude that the pair Gn, where n is abelian, this pair does not admit the Post Lie algebra structure. Okay, I'm sorry, I will not go into detail about the proof of this theorem because this would take me too long and it's rather technical, but at least I can already start by filling up the scheme. So it says n is abelian, the first column. Yeah, and the case that we are working with a semisimple Lie algebra. Yeah, and also a simple Lie algebra is included in the setting. So these two guys, yeah, if you have a G which is simple or semisimple, will never allow a left symmetric structure. Yeah. So now I'm left with the nilpotent ones, which are not abelian, solvable ones, which are not nilpotent, and reductive ones. So what can I say about these cases when n is abelian? Well, so suppose n is nilpotent, sorry. And not abelian, so nilpotent one which is not abelian. Well, it is certainly not true that for any, well, sorry, I have to say G. Yeah. G is nilpotent and non-abelian. Certainly it's not the case that for any nilpotent Lie algebra we can expect to have a left symmetric structure. Yeah? But the aim I want to show is that at least some nilpotent ones do have a left symmetric structure. Yeah? And for example, an easy example is the following. Suppose G, so the Lie algebra with the square brackets, is two-step nilpotent. And non-abelian. Okay? So this means that if you take triple brackets, everything becomes zero, but there are brackets in this set that this one is not zero. Okay? Well, then we can define the product x dot y just as being half of the bracket. And then it's easy to check that in this case, the two conditions are satisfied. So let me look at 1 and 2. Well, 1 just says that this should be equal to x dot y. So this is 1/2 of xy minus 1/2 of y dot x. So minus 1/2 yx. And of course, we know that if we change x and y, we have to change the sign too. So indeed, this is correct. So this is done. And the second one is actually trivially satisfied because, for example, x by z is nothing else than x by z, which is 0 in the nilpotent one. And also all this product will be a triple bracket. This product will be a triple bracket. So this term is 0, this term is 0, this term is 0. So I just get trivially that 0 equals 0. So this means that indeed this nilpotent Lie algebra has a left symmetric structure. Yeah. And in fact, many nilpotent Lie algebras have a left symmetric structure. Yeah. Remember my class of yesterday? So I introduced or I explained the connection between left symmetric structures and simply transitive affine actions. And for a long time, it was thought that all solvable Lie groups admitted a simply transitive action. So this means that all solvable Lie algebras would admit a left symmetric structure. So this was believed for a long time. Yeah, but we have seen that by the results of Boudoir and Buddha and Grunewald, this is not the case. So many of them have such a structure. This is just a simple example. And so this means that in my scheme, yeah, let me put it back. So we know that there are examples, yeah, of G nilpotent and abelian, and we have a post Lie algebra structure on this tuple or this pair or a left symmetric structure on G. The next case is, what about the case that G is solvable? But as I just said a few seconds ago, it was for a long time believed that all solvable algebras admit left-symmetric structure. So at least there should be one example. And let me show you an easy example, the most easiest one we can find. So we have to consider a solvable algebra which is not nilpotent. So you already find this one in dimension 2. So take G to be the space generated by two basis vectors. Let's say E1 and E2, and you have read bracket E1, E2 equal to E1. Yeah. And now define the product, bilinear product, by defining it on the basis vectors. So I put E2 times E1 equal to minus E1, and then all other products between basis vectors I put equal to 0. So E1 times E2 is 0, E1 times E1 is 0, and E2 times E2 is 0. Now again, I have to check if the conditions are satisfied. So let me do this. So we need that, first of all, xy has to be equal to x times y minus y times x. And so, since I'm working with the bilinear product, it's enough to check this condition for x being equal to E1 and E2, or E2 and y equal to one of the basis vectors. If I do this for all possible combinations of basis vectors, I'm done. Of course, if x equals y, I have 0 on the left-hand side and 0 on the right-hand side, so I do not have to check this. So it's enough to check the condition for E1, E2, and the other one will follow automatically because this condition, if you change y and x, you just get minus the previous one. So it's okay to check it only for this condition. And so this should be equal to E1 dot E2 minus E2 dot E1. And indeed, this guy is E1. E1 times something, yeah, this is always 0. And this one, E2 times E1, I have chosen to be minus E1 with the minus sign over here. I get indeed that E1 equals E1. So this condition is okay. And then the second condition, says that xy times the bracket of xy times c have to be equal to this combination. And again, I have to check this only on basis vectors. So I take all possible combinations of this form. And I have to check that this is okay for all possible choices of I, j, k between 1 and 2. Okay. First fact is that if I is equal to j, again, this term becomes 0, and of course, these two terms are the same. You subtract them from each other if I equals to j, so the right-hand side also becomes 0. So it's easily satisfied when I equals j. Now suppose that I is different from j. So this means, that the pair ij is just the pair 1, 2. One of them is 1, one of them is 2. Okay. Certainly, this bracket, then the bracket is something in E1, and E1 times something is 0. So the left-hand side is certainly always 0, for whatever choice you make of ijk. Now, the right-hand side, one of those two is 1, but E1 times something is 0. So certainly, if this one is 1, then this term is 0. If this one is 1, then certainly this term is 0. So this term is 0, and for the same reason, this term is also 0. So I get trivially that 0 equals 0. And so this is an example of a left-symmetric structure on two-dimensional solvable Lie algebra G. Yeah, it's indeed solvable because you only have dimension 1 over here, so brackets of d1 and d1 is 0. It's not nilpotent because if you keep bracketing, you keep having e1. So just bracket e1 with everything, you get again e1. So it's not nilpotent, but it's solvable. And so this means that this is an example of a solvable non-nilpotent Lie algebra admitting a left-symmetric structure. Now, what about reductive? Yeah? You could imagine that reductive Lie algebras, somehow they are semisimple plus some abelian part, that they should be close to the case of semisimple. Well, as we will see in the story of Post Lie algebra structures, they sometimes play a special role. And also in this case, we can find examples of reductive Lie algebras that do admit a left-symmetric structure. And actually, the example is extremely easy. So, what about G being reductive? Well, take G to be equal to G and C, or whatever field you like. Yeah, this works over any field. And then take the product x dot y just being equal to xy, which is matrix multiplication. So you just take matrix multiplication. And by definition of this Lie algebra, we do have that the Lie bracket is given by xy equals to this combination. Yeah. And then it's also easy to check that the second condition will be satisfied because the product will be associative. And so you will be able to use this for this example. Yeah. Okay. The reason that this does not work for SLNC is, of course, the reason that the product is just not matrix multiplication is just not internal inside SLNC. Yeah. So, as a conclusion, we have that also for the reductive Lie algebras, we can fill up our scheme. And so I can put a check mark over here. And in this way, I have filled up the first column. Okay. The next step I will do is now fill up the first row. And actually, I will continue now from now onwards, row by row. So I will look at the situation now where G is abelian and look at all possibilities for N. So maybe I write for B, what if G is abelian? Okay. Then, as explained already in the first class, Post Lie algebra structure, or Post Lie structure for short, on Gn corresponds to an LR structure on N. So to be precise, we ask that minus xy, curly brackets, is now x dot y minus y dot x. Okay. For the LR structure, we should have this, but that doesn't matter too much. Okay. And then left multiplications and right multiplications should commute. So this should be the same as this. And thirdly, this should be the same. Sorry, y. For all possible x, y, z, of course. So a post algebra structure or an LR structure on N or on the pair Gn corresponds to a product satisfying these three properties. And now I will prove the full result that we need. So I claim, let's say theorem. And from now onwards, if I do not mention any name connected to result, so if I put no name, then this is joint work between myself and Dietrich. So for once, I will put our names, but I will probably forget in the future. So all the results that I mentioned without any name are results of me and Dietrich. Yeah, and you can find them in our papers. So paper 41, 44, and 51 on Dietrich's homepage. So the result says the following: if n, let's say, admits a bilinear product satisfying 1, 2, and 3 above or to the left, so actually meaning that admits a left a large structure, then the Lie algebra and has to be two-step solvable. Just not only solvable, but two-step solvable, or solvable of derived length 2. So by this I mean that if you take the bracket of n with itself, and then you take the bracket again like this has to be 0. Okay. So if we have a product like this, I claim then the Lie algebra has to be two-step solvable. Now let me give the full proof of this result. And so let me first of all just pick 4 random elements in the vector space, in N, okay? And let me make a small computation. So I put xy times uv, and the only thing that I will use in the computation is property 2 and 3. So I will use that left multiplications commute and right multiplications commute. And I will use these properties in turn. So first of all, I will use that right multiplications commute. So this means that I can interchange these two elements. So it is the same as x times uv times y. And now I will use that left multiplications commute. So I use the left multiplications on these two. So this means that I can put, or on these two, that I can put u in front, x over here, and then y over there. Now again, I use that these two, I can change places. I hope I will not make any mistake during my computation. So this is uy times xv. Now I use again that left multiplications commute. So this means that I can change these two. So this should be equal to x times uy v. Now again, right multiplications commute at this point. So well, let me continue over here. Yeah. So I can interchange. So I have x times, and I can change y and v like this. So this is u v y. I just interchange these two. And now again, left multiplications commute. So I can change this and I get uv times xy. And now what is the fun thing that happened is that if you look at this part, this is equal to this part. So I have xy times uv is the same as uv times xy. So the product of two elements commute with the product of two elements. So conclusion over here. If alpha and beta both belong to n dot n, so they are elements that you can write as a linear combination of products, a linear combination of, let's say, products of form xy, then these two elements commute with each other. So this means that alpha times beta equals beta times alpha. Now, this also means that if you look at the bracket of alpha times beta, well, by definition, the bracket is, well, minus the bracket is alpha times beta minus beta times alpha, which is 0 because the two elements commute. So the bracket of two of these elements will be 0. Okay? But of course, if you look at the bracket of n times n with itself, this sub-algebra, any bracket is of the form something dot y minus y dot something, well, minus the bracket. But you see that this is a subset of n times n. And so as a full conclusion, we get that n bracket with itself is a subset of n dot n, bracket with n dot n. Okay. And here we see that if you take elements of n dot n and you take brackets, that this is 0. So this is 0, showing that my claim is true. If I take the bracket of nn with itself, I get 0. So this is solvable of derived point 2, and this proves the theorem. And this allows me again immediately to put some crosses in my scheme. So I'm working the case that G is abelian. Okay. Then I know that if I have a Post Lie algebra structure, a large structure, okay, then the n has to be two-step solvable. So it has to be one of these three. So it cannot be simple, semisimple, or reductive because these are not two-step solvable. Already three elements vanish. Okay. And then what about the nilpotent ones and the solvable ones? Well, I can take more or less back the examples I had before. So, if n is two sets for nilpotent, and it's certainly also two-step solvable. Yeah. Then we can again define the product x times y as 1/2 of the bracket. Well, to be really correct, minus 1/2 on the bracket, and then you will see that minus the bracket is again what we had, just exactly the same computation as I did some time ago. Yeah. And also, these two will be automatically satisfied because you get triple brackets which are 0. So two-step nilpotent is not a problem. And also, if n is again the two-dimensional, sorry, now curly brackets, solvable Lie algebra. Yeah, the solvable two-dimensional Lie algebra, which is not nilpotent. Yeah, then as a product, we should take, well, let me see, the 2 times E1 should now be just E1 to get the minus sign over here, and all the other products should be 0. And again, you check that the conditions are satisfied exactly the same way as I did, let's say 10 minutes ago in the other case. So as a conclusion, I can fill up completely the first row. So indeed, we do have examples of abelian and nilpotent algebras together having post Lie algebra structure, and of abelian and solvable algebras having the post Lie algebra structure. So time to go to the second row. So now I will consider the situation that G is nilpotent. And as you see, it gradually gets more and more complicated. So what about the case that G is nilpotent? This is C. G is nilpotent Lie algebra. And so, in order to deal with this case, I have to go back to results of a person called Goto. And this is a result already from 1968, if I'm correct. Well, I think I even wrote down 1962. And this says the following. So let me write down a lemma. And the lemma says the following. Let S be a semisimple Lie algebra. And suppose that N is a nilpotent subalgebra of G, then you can see that the dimension of N, 2 times the dimension of N, is strictly less than the dimension of S. And actually, Goto even proved a stronger result. Yeah, he says that this is smaller than the dimension of S minus the rank of your semisimple Lie algebra, but I do not need the sharp bound. I just need this inequality. Yeah? And maybe it's good to have a very quick look to an example. Yeah? For example, if you look at SLNC, yeah? So you have matrices, yeah, of this form with traces equal to 0. Well, a standard nilpotent subalgebra is, for example, looking at all upper triangular matrices with zeros in the diagonal. So this is typically a nilpotent Lie algebra, which is a subalgebra of SNC. And indeed, you see that the dimension of this Lie algebra, the number of components over here, is strictly less than the dimension of S, because, well, here you have already the same amount of dimension, and then you can add up even more. Yeah? And this is the typical thing what happens with simple or semi-simple Lie algebras. Now, then Goto used this lemma to prove the following result. Namely, he says the following. So let me call this a theorem. So this is still from the paper of Goto, and says the following: if G is N1 plus N2, where N1 and N2 are nilpotent. Subalgebras of G. Yeah? So G is a Lie algebra. Then G has to be solvable. So what I mean with this is just the vector space G is the sum of the vector space N1 plus the vector space N2, but N1 and N2 are nilpotent subalgebras of G. So if we can write G as a sum of nilpotent ones, G itself has to be solvable. Okay, and the proof is now easy once you know this lemma. The lemma is a little bit harder to prove. So the proof goes as follows. So suppose G is not solvable. Then G can be written as R semi-direct S with R the radical of G and S non-trivial semisimple part, semisimple subalgebra. And now we can consider the natural projection from G to S, so just project down onto the second component. And then it's obvious, yeah, if G is the sum of those two, then it follows that P of G, which is S, has to be the sum of P of N1 plus P of N2. Just project down the two ones. Now these guys are nilpotent subalgebras of S. And so it follows that the dimension of S is at most the sum of the dimensions of these two subspaces. And now by the lemma, if we believe this lemma, the dimension of the nilpotent subalgebra of S is at most slightly less than half of the dimension of S. So this means this is less than 1/2 of the dimension of S plus 1/2 of the dimension of S by the lemma. And then we get a contradiction saying that the dimension of S is strictly less than the dimension of S itself. So this is a contradiction, meaning that the fact that G is not solvable is not correct. And so conclusion, G has to be solvable. So fact, yeah, if you can write a Lie algebra as a sum of two nilpotent subalgebras, it has to be solvable. Actually, Goto proved more in this paper. He proved also the converse. If G is solvable, then you can always write it as a sum of two nilpotent subalgebras. Now, it's a very nice paper to have a look at. It's only 2 pages long, but I think it proves a very nice result on Lie algebras. Okay, and now we're going to use this result in the situation of post Lie algebras. So let Gn be a pair of Lie algebras. And assume that M is nilpotent. And that there is a post Lie algebra structure on Gn. So, then G has to be solvable. So we had this when n was abelian, We also have that G had to be solvable, actually two-step solvable. Yeah. Now we can conclude that if n is nilpotent, then G also has to be solvable. So we cannot reach simple or semi-simple or reductive Lie algebras in this setting. Now the proof goes as follows. Recall that if dot is a Post Lie structure on Gn, then we have that the map, let's say phi going from G to n, semi-direct derivations of n, sending x to x, comma, L of x is a morphism of the algebras. Actually, we had a one-to-one correspondence, as I explained yesterday. If you have such a map, which is Lie algebra, homomorphism, and every L of x really sits inside the derivations of n, then these maps correspond to the left multiplications of a Post Lie structure. So we have this situation. Sorry, I'm wrong. I have to suppose I'm in the situation that G is nilpotent, and I have to conclude that n has to be solvable. Yeah? I'm working on the row that G is nilpotent. Yeah, it's this row that I'm doing. I want to prove that n has to be solvable. Okay, so I have this proof, and now let me introduce H, subalgebra of the derivations of n. Yeah, so just the set of all L of x when x belongs to G. Okay? So you take the set of all possible left multiplications that you have, and of course, this is a homomorphic image. Okay? So L goes from G to H, sending x to L of x is a Lie algebra. Homomorphism. Okay? This is the map phi, and then projecting down onto the derivations that you do. Okay? So you have Lie algebra homomorphism. Okay? And so we have that phi of G is sitting inside n semi-direct H. Okay? So I just take all the possible L of x's. Now I claim that n semi-direct H is the same as phi of G plus this H. This C inside here. So I see H as a subspace of the semi-direct product. Yeah, and I claim that this Lie algebra is the same as this one. Okay, the proof is not easy. It's not so difficult. So take an element inside here. So take any x in n, any and y from this space n semi-direct H. So I take an x over here, an L of y over here, and this forms this double. Then x L of y is the same as x L of x plus 0 L of y minus L of x. Okay. And so, of course, this element is an element of phi of G, and this element belongs to H and seen as a subspace of the semi-direct product is this totally an element of H. And so any element from this space is sitting inside this space, and vice versa. If you take an element from this space, so there's an element of the form L of x plus an element from H. So if you take an element over here, yeah, then of course, if you look at this, this is just x, L of x plus L of y, well, this is, which is the same as x0 plus 0 L of x plus L of y. So this is an element of n, and this is an element of h. So this is an element of n plus h, which is the similar product over here. So I have shown that these two spaces are the same. And then we can conclude that n is of course a subspace of n semi-direct h, which is the same as phi of g plus h. But now g is nilpotent, and phi is a morphism of Lie algebras. So this is a nilpotent subalgebra of n semi-direct h. But also the h, this is a homomorphic image also of g. It's a subalgebra of a semi-direct product. So also this one is a nilpotent subalgebra of this copying out of this algebra over here. And so we have this Lie algebra, which is written as a sum of two nilpotent ones. So by Goto result, we get that n semi-direct h has to be a solvable Lie algebra. But now the Lie algebra n is a subalgebra of a solvable Lie algebra, and so as a conclusion, we get that n is itself solvable. And so this theorem now allows me to add some more crosses to this scheme, in the sense that if G is nilpotent, then n has to be solvable if I have a post Lie structure of the pair Gn. So also in this case, the situation simple, semisimple, or reductive cannot occur. And now, what about this case? Are there examples of nilpotent ones and solvable ones which are not nilpotent admitting such a post Lie structure? Well, in order to explain this, let me first introduce a very simple argument. For constructing post Lie structures on pairs of Lie algebras. So suppose Gn1 is a pair of Lie algebras. Admitting, let's say, a post Lie structure, and we'll get the word algebra from now onwards. Let's say structure dot. And you have that G2 N2 is also a pair of Lie algebras admitting a post Lie structure, which I denote by, let's say, circle. Well, then quite trivially, if you take the direct product of the Lie algebras, this will be a pair of Lie algebras. Also admitting the post Lie structure, which is a combination of these two, namely the dot on the first factor and the circle on the second factor. So, in other words, if you take x1, y1, and maybe I should do this one with star. So if you define the product of a couple x1 over here, x1 over here, y1 over here. Of course, x1 is also over there, and y1 is also over there. These are the same spaces. So if you define it on the first factor as being x1 dot, and on the second factor using the circle, then this will be automatically a Post Lie structure on the direct product Lie algebras. And the verification is extremely trivial because it's just looking at components for all the conditions. So this is a very easy way to construct examples. And is this now useful? Well, it's useful, for example, to fill up my table. Without having to think too much. So, for example, I know that there's a situation where G is abelian and N is solvable. So let me take G1 in 1 with G1 abelian and N1 solvable and non-nilpotent. And then there is a second possibility. G2 is nilpotent. And N2, well, you can choose one of these two. For example, N2 is abelian. So these examples exist. Now, if we combine them, in the way I just explained, I get G1 plus G2, comma, N1 plus N2. G1 abelian, G2 nilpotent. This means that this one is nilpotent and non-abelian. N1 solvable, N2 abelian. This means that the sum is solvable. And this one was not nilpotent. So this guy is solvable. So I do have an example of a G nilpotent and N solvable just by taking direct products of previous cases. So G nilpotent, N solvable. I can put a V over here, and so this example also exists. Okay, what I'm going to do tomorrow, that's too late to start this now, I guess, is to treat the solvable case. And I can already say that the situation for solvable G will be completely different. So we will not have as many crosses as we have for the abelian and in the nilpotent case. So the solvable case will be much more flexible, and there will be much more possibilities to find examples of Post Lie structures on pairs of Lie algebras G and N. So I think I will stop here and see if there are any questions, and if not, then you can enjoy a break of 5 minutes or so. And thank you for your attention.
Thank you very much for this interesting and nice presentation. Are there any questions or remarks? Are there any questions? No.
I have just a technical comment. Okay. I think it would be better if the light would be different on the blackboard, because it was very difficult to see what was written on the blackboard. It is just a technical. It was very interesting lecture, but it was almost impossible to see what the chalk written on the blackboard because of the light from the window.
Okay,
you can see yourself recording after the lectures, and you can see that on the left blackboard, on the if I stay on the left, if I stay with the face to the blackboard, one cannot see anything you write, and on the right blackboard it is possible because the light from the window or something not reaching there, but you can see in the recording then.
Yeah,
so if you can tomorrow make some light, or maybe put some curtains in the window, or put some light on the board, so that what you write is better seen. I think it would be appreciated.
Okay, I have the recording. So the same thing was like this yesterday?
I'm not sure. Yesterday, I think it was. I didn't notice it, but now I really cannot see what is written on the left blackboard. So maybe change light from the window changed or something. I don't know. From the window.
Of course, I'm very depending on the weather in Belgium, which is.
Just take a look at the recording and see if you give it the same as. Okay, thanks.
Okay, I will have a look at the recording. Let's see if I can do something about this.
Just to reassure you, Karel, it was fine for me. I saw everything. Maybe it's different according to different computers. I saw everything on the blackboard.
Yeah, I'm not sure how about us.
Yeah, I cannot myself see any difference on my screen between left and right.
I see on the screen, then I can see what is on the right blackboard, which is near the wall and near the window, but I cannot see what is on the left blackboard because it's dark and not that what you wrote is not. I cannot see. So I think it could be different for different computers, and so different people might experience some different things. I don't know what's the situation. But it's very interesting, especially with semi-direct product application to apply semi-direct product in general to figure out this questions. So it's very interesting. Thank you. Take a look at the light.
Okay. So thank you for this comment. I will have a look at the recording, but for the moment, when I look to my screen, I must say that I do not see a difference really between left and right. So, but I will see if I can find some more light to put on the blackboard.
But let me just give a positive joke. In your lectures and theorems, the difference between left and right is very clear.
Okay, thank you.
So,